Hello, Physics 2. Here's the next part of the chapters 15 and 16 slides. So do now, where does the Vice President live? The Vice President lives at the U.S. Naval Observatory. And that kind of leads into part of the answer to question 2. What evidence for time dilation and length contraction did we discuss last class? Well, we discussed two. One was the deal with the atomic planes. I'm sorry, the atomic clocks. We don't have atomic planes yet. Atomic clocks on planes. So that's where some scientists synced up their very, very accurate atomic clocks with those at the U.S. Naval Observatory. They put clocks on planes, sent them around the world in opposite directions, brought them all back together. And the clocks that were on the planes were now out of sync with the clocks at the U.S. Naval Observatory. And the amount of being out of syncness perfectly agreed with the predictions of special and general relativity. General relativity we haven't got to yet, but we'll talk about that eventually. So that proves that there's something to relativity. And the other thing we talked about was the muons. So, the muons are those particles created way up in the atmosphere, and they shouldn't live long enough to reach the ground, but they do. And from the ground's point of view, it's because of time dilation, and because of the muon's point of view, it's because of length contraction. So we also talked in the last class about that very cool paradox, which is my favorite paradox out of all these things, about the train that's the same length as the tunnel, and it's going to go through the tunnel, and then the guillotines drop at the front and the back at the same time, and it's all about the relativity of simultaneity. So that's my favorite paradox. This paradox is really the most famous paradox, the one that we're about to deal with, the twin paradox. So we've talked a little bit about two twins, 17.0-year-old Alice and Denise. Denise stays on Earth. Alice flies off to Vega. So first, from Denise's point of view, Denise says that she is standing still. Alice is the one that's moving. Moving clocks run slower. So Alice's clock is running slower, and therefore Alice is aging too slowly. This is according to Denise. And so Denise would be standing by this clock. Alice's clock is moving off to the right. From Alice's point of view, kind of the opposite is true. Alice says, no, me and the spaceship, we're sitting still, and I'm not moving to the right. Denise is moving to the left. So notice the speed lines to the right on Alice's rocket ship, because this is from Denise's point of view. And on this slide, the Earth and Denise, they're all moving to the left. So this is from Alice's point of view. I'm sorry, I think I said it backwards before. Anyhow, from Alice's point of view, she and the spaceship and their light clock are standing still, and Denise is moving to the left. So according to Alice, Denise has the moving clock. So time dilation is happening to Denise. So Denise's clock is running too slowly. Denise should be aging too slowly. So that's all fine and good that they, disagree at this point. But what happens if Alice flies off to Vega and immediately turns around and flies back to Earth? Each one has been saying that the other's clock is running too slow, and therefore the other one should be younger. So when they get back together, is what's actually the truth? Is one of them younger? Is one of them older? Or are they still the same? So the question is, which twin is older when they're reunited? And the answer is Denise. Denise would be older when she's reunited. So the paradox is, again, both people say that the other one's clock was running too slow. Therefore, the other one should be the younger one. And that can't be true when they get back together. They can't both be younger than each other. It turns out that one of them actually is younger, and Denise is older. So what's really going on here? So then we watched this video, and it explained it. And in a nutshell, the key is this is not as symmetrical a situation as it seems. Again, it's not as simple as Denise says, oh, Alice is going to the right, and Alice says Denise is going to the left. That seems very symmetrical. The thing that breaks the symmetry is the fact that if Alice is going to go to Vega and come back, Alice has to accelerate at some point. So she will no longer be in an inertial frame of reference. And that's what breaks it, because remember, special relativity only deals with inertial frames of reference. So if Alice slows down when she gets to Vega and then stops and then speeds up and goes back the other way, that's one form of acceleration. If she just does a quick loop around Vega and keeps the same speed, she would still be changing velocity because she's changing direction. So that is also acceleration. So that is the thing that breaks what am I saying? It breaks the symmetry. Yeah, because when Alice is accelerating, special relativity doesn't apply because she is no longer in an inertial frame of reference. And in fact, Denise will be older when Alice returns. So, yep, there it is. And then the other thing we looked at, let me try to go kind of quickly through this, is relativity, special relativity at low speeds. So we keep talking about people flying by at 50% or 80% or 99% the speed of light. How does special relativity apply if you're just going at regular speeds? So we're going to say that you are going to drive 3 kilometers, 3,000 meters, to Charter Arts, and you're going to go at 30 meters per second, which is about 60 miles per hour, and it is 0.0000001 c. So this is a very, 60 miles an hour. That's an everyday kind of speed. That's something we deal with. And we're going to look at, the calculations and the predictions according to Newton and according to Einstein. So starting with Newton, Newton says, yeah, length is length. There's no such thing as proper length and observed length. 3,000 meters is 3,000 meters. That's all there is to it. So Newton would plug in the definition of velocity, solve it for time, and say that 3,000 meters divided by 30 meters per second will give you 100 seconds. So it takes a minute and 40 seconds for you to make this 3,000 meter trip. So nice and simple, according to Newton. For Einstein, it's a different story. Einstein says, no, there's length contraction, there's time dilation, there's weird things going on. So here's Einstein's length contraction formula. And if you plug in for the ugliness and you try to turn this into a number, again, your handheld calculator is not going to be willing to do this math to you because the difference you're going to come up with when you square 0.0000001, you get an even tinier number. And if you subtract that tiny, tiny number from 1, you get a number that's so close to 1 that your calculator doesn't even care that it's different. Basically, it's past the accuracy that your calculator keeps. So yeah, you get this tiny, tiny, this number that is so very, very slightly different than 1 is what you get. So you plug it in, and 3,000 meters, that's the proper length, and the observed length is this number that is so very slightly different than 3,000 meters. So if we wanted to figure out the time, we don't have to do the bit with the ugliness again, because now that we know the observed length, we can just plug it into the definition of velocity, and we get this time, 99 point many, many nines, 5 seconds. So here are their predictions, and notice how very slightly different their predictions are. So for example, in terms of the length that is traveled, Newton and Einstein's predictions differ by just this tiny, tiny number, which is 1/7 the diameter of a hydrogen atom. So over this 3 kilometer distance, the difference is only a fraction of the width of a single atom is what's happening. And time-wise, they deal way out here. So this amount of distance and this amount of time, they're basically impossible to even measure. But the key here is Newton and Einstein would have made different calculations and different predictions, almost identical, but very, very slightly different nonetheless. So who is right? Einstein is right, and Newton is wrong. So yeah, surprise, everything I taught you last year was kind of a lie. But it wasn't much of a lie. It was a lie that was so very, very close to being true that it boggles the mind how slightly different my lie and the truth actually were. Which brings us to this. So this is one of the vocab terms I'm going to want you to know by the end of the chapter, the correspondence principle, which says the predictions of special relativity correspond to the predictions of classical mechanics at speeds much lower than the speed of light. So what, the whole point of this is from the time of Newton up to the time of Einstein, we had been using Newton's physics, and they worked really, really well. So if Einstein were to come up with a new theory, special relativity, it had to pretty much agree with Newton's, ideas in the realm where we were testing Newton's ideas, because Newton's ideas really worked very well. So yeah, you start to get weirdness if you're very close to the speed of light, but if you're going much slower than the speed of light, the relativistic effects don't really matter very much. And it all comes down to this term. So we're going to look at the behavior of this term under the conditions where v is much less than c. So our velocity is much lower than the speed of light. And mathematically, this is handy to know. You'll see this, in math and science in the future. V is double less than c. That means if v is much less than c. So it makes sense. Well, if v is much less than c, then v squared over c squared is pretty close to 0, and therefore the square root of 1 minus v squared over c squared is pretty close to the square root of 1 minus 0, which is just the square root of 1, which is just 1. So if your velocity is much less than c, you don't have to make a very big correction at all. You make an incredibly tiny correction to the ideas of Newton to get the right answer. It's only when v is close to c that this term starts to be a thing that you have to worry about. And as a handy rule of thumb, you have to be going about 10% the speed of light for this term to make a 1% difference in your answer. So at normal everyday speeds, keep using Newton's physics. It's only when you're getting closer to the speed of light that you need to worry that Einstein's physics are actually more correct. And again, the key is it's not that Newton is exactly correct up to a certain speed, and then all of a sudden Newton is wrong and Einstein is right. Technically, Einstein is always exactly right with this stuff, and Newton is only approximately right when you're at speeds much less than the speed of light. Hopefully this is making sense. I'm explaining it very wordily, but hopefully it's making sense. So yeah, most of the time Newton's physics is very, very accurate. So accurate that the difference between what it's saying and what is actually true is just really, really hard to even comprehend. Whereas Einstein's physics is always exactly right. So far. Turns out special relativity won't be completely exactly right once we start learning about general relativity. And then it'll get even more complicated and more messy once we start worrying about quantum mechanics. So I will put the link to all of these videos here in the description. So Crash Course, I mean, it's good. It explains it. If you want a review of these things, you can watch that. Yeah, the twin paradox one is cool. Last class is when we watched about the relativity paradox with the train in the tunnel. And this last video here, it's the derivation of this square root of 1 minus v squared over c squared. So if you're interested in how these things are derived and like where did this thing come from, yeah, watch that video. It does a good explanation of that. That's it for this time. Hopefully you found that helpful.